So for electron configurations, we've got the SPDF method, and that's where we read it off the periodic table. And the method is to read and then rearrange as necessary. And then there's the noble gas SPDF method. And then there's the noble gas orbital box diagram.
Right.
And sometimes the book says orbital box noble gas, but it means the same thing.
Okay.
And then, of course, there's the orbital box by itself. So examples of all of these very quickly would be, for example, iron. So iron, you would read 1s2, 2s2, 2p6, 3s2, 3p6, then you'd go 4s2, then it would be 3d6 for iron. Iron has an atomic number of 26, I believe. And when you add these all up, the first three, 2, 2, and 6 add up to 10. The next three, 2, 6, and 2 add up to 10. So that's 20 and 6. So that's the first part you would do for iron. And then to rearrange, you would write 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, and then 4s2. The point is that you want to write all the ones first, then the twos, then the threes, then the fours, and if there are, then the fives. So that's the rearrange part. Now, for the noble gas for iron, you would start with the preceding noble gas that comes before iron. So that happens to be argon. And argon has 18 electrons, and that would be these electrons that you can see right here that are in the 1s2, 2s2, 2p6, 3s2, and 3p6. They're all part of argon. And then you would read from the periodic table, and you would read 4s2, 3d6, and then you would rearrange this also, and you would get argon 3d6, 4s2. So this is the noble gas SPDF notation. The noble gas orbital box notation looks as follows. Argon, and we're going to use this. A D subshell has 5 orbitals. 1, 2, 3, 4, 5. So that's the 3D. And you put electrons in there, and you put 1 electron per orbital. Because the deal is according to Hund's rule, when you put electrons in these orbitals, you want to put 1 per orbital if the orbitals are all the same energy before you pair them up. So since we have 6 electrons, I've used 5. I now have to pair these two up. The reason we don't like pairing them is because you're sticking 2 negative charges in the same orbital and they repel one another. So it's not a great thing to do when you can put them in other orbitals. But at this point, we don't have any other orbitals to stick them into that are the same energy. And then the 4s2 would look like that. Now the orbital box diagram, I don't want to draw out, but you'd have 1s2, 2s2, 2p6, and you'd have that all drawn out. So that's the electron configuration of atoms in a nutshell. Now, the electron configuration of cations, you actually start with the neutral atom, and then you take away the less stable electrons equal to the charge. So if the charge is +1, you take away 1 electron. If the charge is +2, you take away 2 electrons, and so forth. So when we take a look at two very common iron ions, there's iron 2 plus and there's iron 3 plus. So iron 2 plus, we would take a look at this configuration here. I'm going to look at the noble gas SPDF method. For 2 plus, we have to take away 2 electrons. So the least stable are the 4s electrons. So you would write argon 3d6. And for iron 3 plus, you would write argon 3d5. So that's the electron configuration. I forgot the word configuration there, of cations. Any questions so far?
No, yeah, I do understand this part.
Okay. And then lastly, the electron configuration, just so that we finish it all, of anions. It's going to be the same as the electron configuration of the noble gas in the same period. And there's a reason behind that. The reason behind that is noble gases are inert. And that means they are unreactive. And another way to say unreactive is that they are stable. So there's something special about the electron configuration of a noble gas. So when you look at, say, the electron configuration of neon, 1s2, 2s2, 2p6, there's something really stable about this. When you look at the electron configuration of the carbide ion, it would also be 1s2, 2s2, 2p6. The nitride ion would be 1s2, 2s2, 2p6. The oxide ion is 1s2, 2s2, 2p6, and the fluoride ion is 1s2, 2s2, 2p6. And they say what makes this special is that the noble gases have 8 valence electrons. Valence electrons are ones in the outermost shell in the S and P subshells. Now, when you look at argon, argon is 1s2, 2s2, 2p6, 3s2, 3p6. And when you take a look here, it also has an octet of valence electrons. Now, when we compare that to, say, phosphide, phosphide is also 1s2, 2s2, 2p6, 3s2, and 3p6. So this is stable, kind of like argon is, but it's not quite as stable. And the reason it's not quite as stable is because it's got a charge, so it's attracted to cations. Whereas argon is not attracted to cations because it has no charge. So this P3 minus, the phosphide ion, has a chemical reactivity due to its charge. Okay, that's the electron configuration of anions, okay?
Yep.
Okay, so now we're going to look at periodic trends. And there are 4 basic periodic trends that we're going to look at. And I'm going to list the 4. We look at atom radius. And when we look at atom radius, we're going to look in a period. So we're going to look in a row. We're also going to look in a group. And what we want to try to understand is there a trend in the period? And is there a trend in the group? We're also going to look at ion radius. And here again, we're going to look at a period trend. And we're going to look at the group trend. We're also going to look at something called ionization energy. Which I like to abbreviate as IE. And we're going to look in a period and a group. And then there's something called electron attachment enthalpy. And I'm going to abbreviate this EAE. And we're going to look in the period and the group at each one of these. Okay?
Sounds good.
All right. So let's look at the radius first. So when we draw an atom like tin, they say that the radius is 141 nanometers. Or is it picometers? I think it's nanometers. I should look it up, huh?
Is it in the book?
Yeah, it's in one of the problems in the book.
Mm.
So I'm gonna, just to make sure that we have it correct, I'm gonna look it up. And it's problem 72. It's 141 picometers.
Okay.
Okay, so what does that mean about the tin atom? It means if it's a sphere, from the middle of the sphere to the edge of the sphere, and that's a 90% boundary, it's 141 picometers. But that also means that when you go from side to side, or edge to edge, if you will, it's 242 picometers. I think I said nanometers, even though I wrote picometers here. So this is the radius and this is the diameter. Any questions there?
Nope.
Okay. So what is the trend in a period? Well, if we look at the book, which we're not going to do, if you look at a lithium, actually a lithium versus a, what's next to lithium? Beryllium, then boron, then carbon, then nitrogen, then oxygen, then fluorine. And we're not going to compare it to the noble gases because it's difficult to measure how big a noble gas is. And I don't want to go into the details there, other than to say that you get these measurements by doing something called X-ray crystallography, which means you need a solid. Noble gases are gases, so it's hard to get a solid. Okay.
Right.
So that being said, when we look at these guys, this is roughly the trend in the size. So if this is lithium, this would be beryllium, this would be boron, this would be carbon, this would be nitrogen, oxygen, and fluorine. So what's happening to the size as we go across the period?
Decreasing.
Right. And what I like to write is this: as Z increases, the radius decreases. So what does Z mean? Atomic number. The atomic number of lithium is 4, beryllium or 3, beryllium is 4, boron is 5, carbon 6, nitrogen 7, oxygen 8, and fluorine 9. So as Z increases, the radius decreases. Now, what is the reason for that? And to understand why this is the case, we look at electron configurations. So lithium is 1s2, 2s1. Beryllium is 1s2, 2s2. And fluorine is 1s2, 2s2, 2p5. Now, the reason I just jumped to fluorine is that you can see pretty quickly that the outermost shell is the second in each one of these. And the reason we want to know about the outermost shell is because the outermost shell really sets the diameter or the radius of the atom. This measures to the 90% boundary for the biggest shell that has electrons in it. So they all have the same outermost shell, so it's kind of hard to decide which one's going to be larger. And you might actually think, since fluorine with its 9 electrons has more than 3 electrons, it's going to be spread out more. but that's not the case. What actually happens is that when you look at the Z, we've got 3, 4, and 9. So here's the way it works. When you have 3 protons in your nucleus, when you have 4 protons in your nucleus, and when you have 9 protons in your nucleus, and you're pulling in that outermost shell, the 9 protons is going to pull in that outermost shell more tightly because there's more protons attracting the electrons in that outermost shell. The 4 protons are going to do a worse job, and the 3 protons are going to do an even worse job. So you see what kind of determines the diameter or radius of the atom are 2 things: the outermost shell and the number of protons in the nucleus. When the outermost shell is the same, more protons makes for a smaller atom.
So it's the opposite of what you would think it would
The
be.
opposite of what you would expect, because you would say, you know what, hey, with more electrons in there, they're fighting for room, they're going to spread out.
So it's generally because basically because of the nucleus, because of the protons, they're kind of like bringing in the electrons.
Yeah, think of that, the nucleus being a magnet.
Yeah. Mm-hmm.
9 protons is a bigger magnet than 3 protons, so it's going to pull in the other electrons in better. 9 protons, that is.
And that's throughout the entire periodic table.
Yeah, that's from left to right for any period. Now, there are some glitches where it doesn't work out that well, but it works about 90% of the time. Which I know sounds horrible. It's a science. It's supposed to be left or right, up or down, black or white. But actually, 90% is considered to be pretty darn good for any model in science. It's considered to be very good. And that's one of the problems, is that people don't understand that everything that we do in science is a model of reality. It's not reality, it's a model of reality.
Right.
And when are models as good as reality? And the answer is never.
Right. I think doing that H atom paper yesterday, well, I did it yesterday, but doing that H atom paper was like helpful to kind of understanding like the process of like science and
how a model is developed. A model is developed based on reality, and it tries to simplify it so that we can see something there, see a pattern. Okay. All right. So that's the period trend for the radius. So let's now look at the radius, and let's look at the group trend. So here we're going to look at lithium, sodium, potassium, and so forth. We'll just stop right there, but this would be lithium, this would be sodium, and this would be potassium. They just get bigger and bigger and bigger. Well, this is 1s2, 2s1. This is 1s2, 2s2, 2p6, 3s1. And this is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So when you look at the outermost shell that has electrons in it, it's the second versus the third versus the fourth. So here's the deal with lithium. A 2 is going to be smaller than a sodium with a 3. So we don't really need to look at the nucleus at all. We're just looking at the shell. So potassium, it's an N = 4. So the larger the number of the shell, the larger the atom is going to be. Any questions there? Remember, when you look at the shell also gives you a rough idea of how far out it extends from the atom. And 4s extend out farther than 2s, and so forth and so on.
Right.
So this is actually the easier pattern to understand, because here it's only the second shell, here it's the third, and here's the fourth.
Right.
Okay.
Okay. Yeah, I see what you're saying.
Now, let's look at the radius of ions. So first we're going to look at cations, because it's not fair to compare cations to anions. So we're going to look at lithium ion compared to beryllium ion and so forth and so on. It's the same trend. Beryllium is lithium is larger than beryllium. Now, lithium cation is 1s2. Beryllium cation is 1s2. Now, the number of protons in lithium is 3. The number of protons in beryllium is 4. They both have 2 electrons. Beryllium has 4 protons. Who is going to pull those protons in better? Or excuse me, the electrons in better?
Yeah, beryllium.
Because it has more protons.
Right.
So do you see that the cation trend is like the atom trend,
Right.
and for the same reason?
Mm-hmm.
Now, when you look at sodium ion and potassium ion, they just get bigger. Well, why is that? Well, the sodium ion is 1s2, 2s2, 2p6. So here, if you look at the outermost shell, this one is the first, this one is the second. So why is sodium ion bigger than lithium ion? Because it's got electrons in the second shell. Lithium does not. And potassium, what's going to happen here is you're going to have them in the third shell. So it's going to be even bigger yet. So what is the trend going in a group? And the answer is it gets bigger as you go lower. And for the same reason as the neutral atoms. Now, if I do the anion over here, and we look at the, say, nitride ion, and the oxide ion and the fluoride ion, they're going to look like this compared to lithium. Boom, boom, and boom. What do you notice about the anion in the same period as the cation? It's a lot bigger, isn't it?
Yeah.
So why is that nitride so big? And the answer is it's 1s2, 2s2, 2p6. It's got electrons in the second shell, so of course it should be bigger than lithium.
Mm-hmm.
And in fact, you would argue that it should even be bigger than sodium. Okay. So that's the case for all these anions. So in a period, the cation is smaller than the anion. Are you with me there? Cation smaller than the anion?
Mm-hmm.
Okay, in a group, as you go down the group, the ion radius increases. And that's regardless of whether you have anions or cations, because it would be the same thing here. Phosphide would be even bigger than nitride because you have electrons in the third period, or third shell, I should say. So any question about the radius of ions?
No, I think
Now,
I get it.
now what you might be wondering is, do we need to know what the actual radius is? And the answer is no, but you need to know the trends.
Mm-hmm. Okay.
All right. Now, the tough ones, the tough periodic trends are ionization energy and electron attachment and enthalpy. So let's look at ionization energy. So ionization energy is when you have a neutral atom and you apply energy to it, so ionization energy. And what happens is you take an electron off of that atom. So when you take an electron off of that atom, it becomes an ion, and therefore it's called ionization energy. Now, to make this balanced, we have to put the electron over here. So let's take a look at an example of ionization energy at work. If we had a lithium atom in the gas phase and we added some ionization energy, we would end up with a lithium cation plus an electron. So in general, what we're looking at here, here's a lithium atom. Here's the N equal 1, the first shell with 2 electrons on it. And here's the N equal 2 with 1 electron on it, because lithium has 3 electrons. And this is infinity. So if we take this electron here and boost it to infinity and make the lithium atom so that it only has 2 electrons, and you have to remember there's 3 protons here in the nucleus, you basically have a neutral lithium atom with 3 protons and 3 electrons become a lithium cation with 3 protons and 2 electrons. So how do we count for this electron? We say, oh, here it is. So you put a plus there. So that's ionization energy. And as you can see, because the electron is attracted to the nucleus, you have to put energy in to pull it away. So this is an endothermic process. And the change in energy is plus. You have to add energy.
Okay, so that's how you write it. You just separate the electron.
Yep. And I should actually write gas here. So that's how you write an ionization energy reaction.
Oh, okay. Okay. So it's just going out
whenever
to,
we see these arrows.
What does the IE mean? What is the Li plus Li, lithium gas plus ionization energy?
Ionization energy.
Oh, that's obvious. Sorry. Okay. So what would you give us on a test? It would just be like the lithium gas plus ionization energy and then draw it out.
You're going to be asked about trends. So, for instance, when we look at ionization energy, so IE, let's look in a period. So the ionization of lithium versus beryllium versus carbon, boron, nitrogen, oxygen, fluorine, which one's going to have the greatest ionization energy? In other words, which one's going to have the harder electron to pull off?
Is it going to be the one with the most amount of protons? I don't know.
That's it. That's it. So this is going to be the hardest. And this is going to be the easiest. And do you remember the radius of these guys? What happens to the radius as we go across?
It's the opposite, right? It's
they start big and get small. So you can actually do this. So here's big, smaller, 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 and smaller. So they're getting smaller, right? And here we're going to take this electron away. We're going to take this electron away. So we're taking an electron away from the outermost shell. And what you can see, what happens to these arrows is they get longer and longer and longer because the ionization energy is greater. Now, why are these guys smaller? Because they have more protons pulling in the electrons. Now, if you have more protons holding on to those electrons, what does that mean about how easy it is to take those electrons? So I'm going to ask again, if you have more protons holding on to the electrons, what does that mean about taking the electrons?
Yeah, the force is greater energy
Right.
required.
So this is going to be higher ionization energy, and this is going to be lower.
So when you talk about the radius, and I think this is the part that's confusing me, like the radius of what exactly are we talking about? So I know they're getting smaller, but like I'm like, what the radius of what exactly?
The atom.
Just the atom itself? Okay.
So when you look at an atom, here's the nucleus.
Okay, that's the part that I got confused about because I think we were talking about the radius of the atom and then we started talking about the radius of the ions. So that's different.
Well, no, the radius of an ion is the same as the radius of an atom in that your nucleus is in the center, and here, this is where you find electrons. And those electrons are going to be in shells. And that's going to be the case whether you have a lithium atom or you have a lithium ion. You've got the nucleus and your electrons are here.
Right, right.
So your ion has a radius and your atom has a radius.
Right. It's the same. It's just has an electron that has either been removed or added.
Here, an electron's been removed, so naturally you'd expect this guy to be smaller, right? Because here, the outermost shell is n equal 2. Here, the outermost shell is n equal 1. What's going to be smaller, a 1 or a 2?
A 1.
A 1.
Okay.
Okay, so that's the period trend for ionization energy. Now, the group trend for ionization energy. When we look at a lithium becoming a lithium plus 1, or a sodium becoming a sodium plus 1, or a potassium becoming a potassium plus 1, when we look at the ionization energy, this is going to be the smallest, and this is going to be the largest. Now, here is the electron configuration of lithium. And here is the electron configuration of lithium ion. So can you see we're taking a 2s electron?
Yeah.
For sodium, it's 1s2, 2s2, 2p6, 3s1, and it becomes 1s2, 2s2, 2p6, and we're taking a 3s electron. What's easier to take, a 3s or a 2s?
A 2s?
A 3s, because it's farther away from the nucleus.
Okay.
So, you know, when you're looking at the shell, larger shell means farther away. Larger shell means less stable electron.
Right. Okay.
This is going to take you a little while to copy. Well, for potassium, you're taking a fourth shell electron, which is even farther away from the nucleus, which means it's going to be even easier to take. So it's kind of like the same reason why these guys get bigger in size. These guys get bigger in size because they have a larger shell that has electrons in it. But also the larger shell that has electrons in it means it's farther away from the nucleus and therefore easier to take. Okay.
So we're not talking about the radius anymore. We're talking about the shell.
The radius is defined by the shell. Those are interchangeable. When I talk about this outermost shell, this is the radius.
So I guess what sorry, I guess what confuses me now is, okay, so potassium is the larger atom, right?
Right.
So I thought it was harder to take an electron from a larger atom.
No, see, now you're confusing ideas.
I'm confusing ideas, yes, that's why I'm confused.
The idea is that when you go across a period, you care about how many neutrons or protons.
Right, exactly.
So here, when you go left and right, you care about protons. But when you go up and down, you care about shell.
Oh, okay. Okay.
So you're applying protons to the up and down trend, and that's wrong.
So the trend across, okay, so they're completely two separate things. They can't be like, they're not mergeable. One does not affect the other.
Not. Absolutely not. And that's why when we look at these trends, from the get-go, we said we're going to look at the period and we're going to look at the group.
Right, exactly.
And then here we were looking at the radius based on the period, and they get smaller going across.
Right.
But for the group going down, they get bigger.
Oh, okay.
So why do they get bigger? Because we're worried about the shell. Here, why do they get smaller? Because we're worried about number of protons. So the left-right is how many protons. Now, the reason we care about protons here is because look at the shell here. The shell is the second. It's always the same. If the shell's always the same, then you can't say, well, they have different shells, and that explains it.
Right.
Over here, if we look at the electron configuration and we look at the shell, they are different. So we can use that as an explanation.
Oh, okay.
The bigger the number of the shell, the larger it is.
All right, okay.
So here, what I didn't draw for you is here's n equal 1, here's n equal 1, here's n equal 2, here's n equal 1, here's n equal 2, and here's n equal 3. You know, they're still there, but the fourth one is the one that kind of defines how big it is. And here there's nothing in the fourth, so it doesn't really contribute to the size.
Okay, so we're looking at two separate things. And I think that's where I got confused as I was trying to like combine them.
Absolutely, we're looking at two different things. So what we're doing is we're looking at a property. And when we say we're looking at two different things, what we're really doing is we're looking at a property based on what's going on in a period versus what's going on in a group. So group up and down, period left, right. Are you there? Are you with me there?
No, yeah, it completely makes sense now. I think I was just thinking that we'd have to look at both things together. So it was confusing me because they seem contradictory.
Well, the one thing you do look at is the electron configuration. So you look at the electron configuration, and then if the outermost shell is different, then that's your explanation. If it's a 2 versus a 3, that explains what's going on. But if the outermost shell is the same, then you look at protons. So when you go up and down, the outermost shell is different. You go from like 2 to 3 to 4 to 5. But when you go left and right, the outermost shell is going to be the third here. It's going to be the second here. It's going to be the fourth here. It's going to be the fifth here. So that's why when you go left and right, you look at the number of protons, but when you go up and down, you look at the outermost shell. Okay?
Yeah, that was helpful.
All right. So that explains the trends for those three. Now here's the tough one. The tough one is electron attachment enthalpy. So here's what happens with electron attachment enthalpy. You have a neutral atom and you add an electron to it. And you end up with an anion. Now, the electron attachment enthalpy is actually energy. And I want you to think about an atom like lithium, which has 3 protons. In the first shell, it's got 2 electrons. In the second shell, it's got 1 electron. And the second shell actually has room for 8 electrons, okay? So here's an electron off at infinity, and it drops down here onto the atom. So we end up with 3 protons as before, 2 electrons in the first shell, and now we have 2 electrons in the second shell. So this would be lithium. This would be lithium anion. Now, I want you to think about this electron here. If I wanted to take it back away, would I have to put energy in to make that happen, or would energy be released?
I'm sorry, if you had to take an electron away?
Yeah, if I had to take it away from this guy, would that require energy or would that give off energy?
I believe taking it away would require energy and putting it in would give energy.
That's right. So here, when this comes down like this releases or emits energy.
Right.
Which means it's exo, which means it's negative.
Right.
So here, where do we write energy if it's a product?
On the product
Right
side?
On the product side. So here, we could also write this reaction this way. And we could say that the change in enthalpy is the electron affinity enthalpy. And this value is negative. So when we say that you have a more negative value, that means more energy is released.
That makes sense.
Okay, so minus 500 versus minus 200, this is more energy released. Okay?
Right. Mm-hmm.
So for what's nice about
do we have to draw those diagrams as well?
It's helpful to understand them, yeah. The reason I'm drawing them is it's supposed to help you understand what's going on.
It does.
And so that means if you can draw them, it would help you to understand them too. Now for electron attachment enthalpy, Nice thing about this is that there's no real period trend. If you look at the data, it's kind of all over the place. It doesn't get smaller, it doesn't get bigger. It kind of jumps up and down. But in the group, here's what happens. When you look at lithium versus sodium, actually, let's look at fluorine versus chlorine versus bromine. This is going to be more negative, and this is going to be less negative. And this is going to be middle negative, if you will. So why are they different? Well, here's fluorine. And fluorine is 1s2, 2s2, 2p6, or excuse me, 2p5, I'm sorry. Chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. Bromine is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, actually I should put 3d10, 4s2, 4p5. Now each one of these is going to get an electron. Where's it going to go? For fluorine, it's going to go into the 2p because a 2p can hold 6 electrons. It only has 5. Chlorine is going to go into the 3p, and bromine is going to go into the 4p. So here, I'm going to make this my second shell. And for chlorine, I'm going to make this my third shell. And for bromine, I'm going to make this my fourth shell. And actually, I want to redraw these. So fluorine is smaller, and chlorine is bigger, and bromine is even bigger yet because they're in the same group. And as you go down the group, they get bigger. So here's your n equal 2, which is where the electron's going to end up. Here's your n equal 3, which is where the electron's going to end up. And here's your n equal 4, where the electron's going to end up. And what I'm going to do here is I'm going to write 1s2, 2s2, 2p5, and this is where the electron ends up. Here I'm going to write neon, 3s2, 3p5, and this is where the electron ends up. And here I'm going to write argon, 3d10, 4s2, 4p5, and this is where the electron ends up. So that's why I have n equal 2 here, n equal 3, and n equal 4. Now your electron is starting here at infinity. So do you kind of understand what's going on here?
Yep.
Now your electron is going to drop to here for F, drop to here for chlorine, and drop to here for bromine. Which of these is going to be a more negative value?
The fluorine.
Right. And we can see that because it's a longer arrow. And this is going to be the least negative value. And I always like to call this one the midlist negative value. It's a pet peeve of mine because in my family, there were 3 kids. There was someone who was the oldest and someone who was the youngest. Well, I happened to be the midlist.
Oh,
I wanted to be S like everybody else. And it's not fair that they're S and I'm not. So darn it, I'm the midlist. And you could even be, you know, you might be thinking, well, what if there's 4 kids? Well, then you can have the elder mid list and the younger mid list.
Yeah, I'm glad you've you've thought of all the possible
Oh yeah, I've thought this through.
options. I'm
Which est are you?
the smallest.
You're the youngest.
Yeah. Well,
Okay.
yeah. Yeah, the youngest.
So the problem with being the youngest is, well, it's a double-edged sword, right? Being the youngest, you kind of have all these older siblings to look up to be examples for you, to kind of to take care of you, if you will. But on the other hand, when you're the youngest and you look at the family albums of all the other kids, the oldest kid has the most family albums, the second less, and the youngest has the fewest.
I don't know. I guess each family is different because I'm the only girl in our family. So it's just
Oh,
I have two older brothers. So like I feel like the dynamics are a little bit different. Plus like they're a lot older than I am. So
oh,
um
so they had some time to recover from the boys and they got to refresh
I don't
and
know. My parents did a really interesting thing where they like separated each of us by like 8 years or more.
eight.
Yeah, like my brother is 14 years older than I am, and then my other brother is 8 years older than I am. So they're like 6 years apart. So it, yeah, that's
Okay.
kind of like a lifetime of parenting.
Yeah, we call that the babysitter plan. You
Yeah,
don't have
one
another
takes care of the
baby
other.
until you don't have another baby until the other one's about ready to be a babysitter.
Yeah, I think that was more so probably to do with more like economics, trying to not have too much burden at once. I'm not sure.
Right, that's the babysitter plan, I'm telling you.
Yeah, yeah.
We kind of did that because we had ours are 5 years apart. And my son did a lot for my daughter, helping to raise her. In fact, there are times when my daughter used to call my son mom, just by accident, mom.
That's so sweet.
Yeah. Um,
That's good.
at any rate, so you were kind of a favorite being a girl, huh?
Yeah, I think it's like I think I just got like more of the better part of my parents.
Ah,
Like it's like they were older. Like it was. I think that I just got the better end of the stick than my brothers did. I can't
they had
deny it.
experience. They had experience by
Yeah.
you. Now, see, for me, I was always the favorite. Um, as soon as I was born, I was the favorite because I'm the only boy.
Oh, yeah. It's
You
like
know,
that.
with dads, they always like the boys. And with my mom, she liked the boys better because she's Japanese. And in her culture, the male child is prized more than the female child.
Yeah. I guess it was.
I'm just saying culture, that's the way it is. I'm not judging it.
Yeah. That's kind of how our culture is too, like Mexican culture. But yeah, for my parents, I feel like they already had two boys, so it's like, okay, well, cool,
Oh,
something
so
different.
they had the one who was going to take over and the spare.
Yeah.
Yeah, for me, I was it. I was like all their eggs in one basket. They
Yeah.
blew it. They blew it big time. All right. So can you see that when we look at the period trend for electron affinity enthalpy, when you go across the period, it becomes more negative, or excuse me, less negative. Nope, I've got this all wrong. Cross it all. When we look at the group trend, when we go down, it becomes less negative, right? Because the way these would be in the periodic table would be fluorine, chlorine, bromine.
Right.
So when you go down, this is less and this is more.
Hmm.
And remember how we said before that when we look at the trends, an up and down trend has to do with the outermost shell.
Yeah.
So 2, 3, 4. And when you go across, it's number of protons, right?
Right.
Well, there is no period trend, so we only have to worry about the group trend, and that's the
Okay.
group trend.
So that's how you determine the energy.
That's right. Now let me see. All right, so let's take a look at some problems that I haven't done yet that in some cases address these issues. So let's look at this one. Explain why the first ionization of calcium is greater than that of potassium, whereas the second ionization of calcium is lower than the second ionization energy of potassium. So here to answer this, we have to look at calcium and potassium and see what's happening with each ionization energy. So calcium, when it ionizes, so I'm going to call this ionization energy 1, is we become a calcium cation plus an electron. Okay? And when we talk about the second ionization energy of calcium, we're talking about this. So this has already had one electron taken away from it. So here's the second ionization energy. And when you take a second electron, you end up with calcium 2 plus an electron. So we take these electrons away in succession, first one, then another. Any questions there?
No.
Okay, so down here, I'm going to do the same for potassium. So this ionization energy 1 is unique to potassium, and it's different than the one for calcium. Okay, so I'm going to end up with a K plus an electron. And then the second one is going to look like this. So how did we analyze ionization energies just a moment ago?
Based on
So
their shells.
where are my ionization energies? Here we go. So how do we analyze these? We basically looked at where the electrons are, right?
Right.
Okay, so let's take a look at what calcium is for an electron configuration. We're going to do the noble gas configuration, but calcium, and actually we're not going to do quite the noble gas configuration. We're going to start with neon, and you'll see why in just a moment. So calcium is neon, and then 3s2, 3p6, 4s2. Fair enough? Potassium is neon, 3s2, 3p6, 4s1. Okay?
Yeah.
Now, what I'm going to do here is I'm going to draw a little arrow
This
to
is for
show
the atom,
you that.
right? Not for the ion. This isn't
What's
for the
that?
cation. Not for the cation. This is for.
Yeah, this is, then that's why I
the
wrote
atom.
TA next to it.
Yeah. Okay.
So when I do the cation plus 1, what is the electron configuration going to look like? And I'm going to redraw this real quick here. So I'm going to write calcium plus ionization energy 1 gives you this calcium plus 1 ion plus an electron. And I think what I'm going to do here is I'm going to write underneath here, neon, 3s2, 3p6, 4s2 becomes neon, 3s2, 3p6, 4s1. I'm not going to worry about the electron. I'm going to just write 4s1. Fair enough?
Mm-hmm.
So this means that we take away a 4s electron.
Mhm.
Now, what if we have calcium plus 1 and we do ionization energy 2? Well, we start off with neon, 3s2, 3p6, 4s1, and what does it become?
Is this the one where we're removing 2 electrons? Then we would have to remove one from the 3p6, so it'd be 3 neon,
Hang
3s2.
on.
Oh,
Why would you take it from the 3p6? Isn't the 4s less stable?
right, but we're removing 2 electrons, right? So we remove one from the
No.
4s1 and then.
We're removing one because we're going from a +1 to a
Okay.
+2.
Right, so we're just removing the 4s1.
So we're going to take away a 4s electron. And this is what you were getting at. You were saying overall, we take 2 4s electrons. That's what you were getting at, correct?
Yeah, I just got confused because I forgot where we were at. Yes, we started
So
off with 4s2.
I just want to do one at a time.
Yeah.
Now for potassium plus ionization energy 1, you get potassium ion plus an electron, and potassium is neon, 3s2, 3p6, 4s1. What does it become?
It would just be neon 3s2, 3p6.
And we're done, right?
Yeah.
Now, when you have potassium and you do ionization energy 2 and you get potassium plus 2, we're going to start with this neon, 3s2, 3p6, and what does that become?
A neon 3s2, 3p5.
Yes, perfect. And here, what do we take away from the first equation?
Oh, the 4s1.
The 4s electron, right? Here, what do we take away?
The 3p6.
A 3p electron, right?
Mm-hmm.
So here we take away a 4s electron and a 3p electron. So remember, this is the second one.
Right.
And this is the second one. And the question is, let's go back to the question. Why is the first ionization energy of calcium greater than that of potassium? So we need to look right here for the first. So here, we're taking away a 4s, we're taking away a 4s. It's the same shell. So what do we need to go to for our explanation?
So if it's the same shell, then we would have to look at the period now.
No, we look at the number of protons.
Right, the number of protons, right? So isn't that
So
the period that we're
calcium,
looking at across?
calcium has 20 protons. Potassium has 19 protons. So we're not looking at the periods, we're looking at the group. This group versus this.
Oh, I thought we were looking across.
We are looking across, but when we look across, what defines things is the number of protons, right?
Right, exactly. Yeah.
Okay, so why
Calcium
is
has more.
calcium greater than potassium?
Yeah, calcium has more protons, so it requires more energy.
So what we would say to answer that is we would say the following. IE1 for calcium is greater than IE1 for potassium because, so we have to set the table here, because in both cases, we take a 4s electron. So that's not the reason why they're different. It's the same, right? But calcium has 20 protons and potassium has 19 protons. Calcium holds the electron better, so it's harder to remove. So do you see how one thing kind of follows the other?
Right. So you're looking at the group first, and then you're
Yeah.
looking at the protons.
So first we're setting the table and saying, hey, they both take a 4s electron. So that can't be the reason. So then we go to the number of protons. This has 20, this has 19. Calcium holds the electrons better. Now, why is ionization energy 2 for potassium is greater than ionization energy 2 for calcium? Well, here we would say, well, potassium, we remove what? Take a look at potassium here. What are we removing for the second ionization energy?
Yeah, so we removed a 4s. We removed
We remove 4s
a
for calcium,
yeah.
and we remove a 3p for potassium.
Mm-hmm.
So we would say for potassium, you remove a 3p. For calcium, you remove a 4s, and 3s are harder to remove because they're closer to the nucleus.
Mm-hmm.
You know, it's kind of like the large herd of antelope or, moose or whatever that is migrating. What gets pulled out of the herd or taken away and eaten? The one that's farther from the middle of the herd. So the closer they are to the middle, the harder they are to take.
Right. Okay.
So that's why whenever you're in a group, you want to be close to the middle, not the outside.
Yeah. Okay.
Okay, so
that was helpful.
That explains that. And what was our go-to to figure out what was going on? Look at electron configurations and see what's being changed.
Right.
So this one is an interesting one also. The densities of elements in group 6b, 8b, and 1b are given in the table below. So if you want to know where 6b, 8b, and 1b are, all you have to do is open up your book and find out where these elements are. So if you look at chromium, chromium's right there, and that's 6b. And if you look at cobalt, it's in 8b, I call it 8BB, if you will. And then in 1b, you have over here copper, right? The weird thing about the numbering here compared to the A's is that the A's are real easy. It's 1A, 2A, 3A, 4A. Beautiful, right? But look at the B's. Do you start at 1B?
3b.
You don't start at 1B. And then you stutter here because when you get to iron, it's 8B, 8B, 8B. And then after 8B, what do? You don't go to 9B, you go to 1B. Luckily, we don't have to memorize the B's. So they kind of tell us that this is 6B. This is the middle one of 8B, and this is 1B. All right. So these are the densities. Transition metals in the 6th period all have much greater densities than the elements in the same groups in the 4th and 5th periods. So these guys have greater densities than the ones previous. Refer to figure 7.8 and explain this observation. So before we even look at the figure, what do we notice about density? Density is what? Mass divided by
Volume.
Volume. Excellent. So we have a suspicion that the reason these densities are so different than the ones above is because the mass is really unusually large, or the volume is unusually small, right?
Mm-hmm.
Now, let's think about chromium, molybdenum, and tungsten. And we think about their sizes. Which one's going to be bigger? The one in period 4, 5, or 6? And when I say bigger, I mean the larger radius.
Oh, okay. The larger radius. Period.
This is
I guess it would
tungsten.
be chromium.
So you think chromium is going to be larger?
The radius.
So chromium is the previous noble gas is argon.
Well, actually, maybe tungsten.
And then you would have for
Yeah, I think
chromium, it would
tungsten,
be,
because you're talking about the shells, right? How
right.
big the radius is. Yeah. Mhm.
So here's chromium. The outermost shell is the 4th.
Yeah. So tungsten.
Here's molybdenum. Molybdenum is 4D4, 5S2. So which one's going to be bigger?
Between those two, or between the three of them?
Between these two.
I don't know how to pronounce that.
It's
Molybdenum.
Yeah. And here's tungsten. Tungsten is xenon. Let's see. 4F14, 5D4, and 6S2. So between the three, which one's going to be larger?
Tungsten.
Because it has stuff in the 6th shell.
Right.
So remember, up and down, it's about the shell. Left and right, it's about how many protons.
I still keep thinking about protons, but it's like.
So here, I'm just going to draw it like this. Here's big, here's smaller, and here's smallest.
Right. Mm-hmm.
How about cobalt? This is rhenium, or rhodium, and iridium. What's it going to be like?
The same. So.
How about copper, silver, and gold?
Same, because they're all in period 6, so they all have 4 shells.
Do you remember how we said with the density here? It's got to be because these guys have a smaller volume. That could explain it. Mm-hmm. But they don't. So why must this have a greater density?
Much larger mass?
Let's take a look at the mass of each of these. What is the mass of chromium? I'm going to round to the ones. 52.
Okay.
Molybdenum, 96. Tungsten, 184. Look at this. This jumps by what? 44? And this jumps by, geez, that's got to be 88. Mm-hmm. That's a big jump. So why is this so much more dense than the others? It's because the mass isn't going up proportionally. It's actually doubling compared to before.
Right.
Normally you'd expect, okay, this should go up by another 44 because they're in the same group, but it doesn't. And that's the case for all of these. So what you would say here is, why do they have greater densities? And the answer is pretty simple. Well, and now we'll look at figure 7.8. Okay, that's not 7.8, that's 7.5. Here's 7.8. So here, this shows the size increase. So do you see how chromium and molybdenum and tungsten have different sizes? And actually molybdenum and tungsten are pretty close to the same size, right? Okay, so you might ask, well, why does it not increase that much in size? Why are these so close together? And the answer is, remember with Bohr's atom, we were supposed to look at the radii and what happens there. They actually get closer together. So here, these don't differ that much in size, but their mass changes dramatically. So when you look at the actual size here, can you see how chromium is about, I would say, 3/4 the size of molybdenum?
Right.
And molybdenum is about the same size as tungsten. So let's use those numbers. So the density of chromium, we're going to call it 1, and the mass is 52, right? So this is just kind of a number to look at. The density of molybdenum, what is the size of molybdenum volume-wise compared to that of chromium? Well, I said that chromium is about 3/4 of molybdenum, but another way to look at that is you could say that molybdenum is like 1.3 times bigger than chromium, right? So I can put a 1.3 here and a 96, and 96 divided by 1.3, and maybe I should say more like 1.5. 1.5 goes into 96 like 70 times. Now for the density of tungsten, you got 184 divided by 1.5 because these are about the same. And here, this goes into that about, I want to say 120 times. So do you see how there's a big jump here from 70 to 120? So how do we put this in words? The words would be something like this. Tungsten has a much greater density because its mass is how do we want to put this? Its mass changes more dramatically than its volume compared to molybdenum. And we would say the same thing about molybdenum compared to chromium.
Okay.
Now, ultimately, I'm going to tell you the reason why it weighs so much more is you've got all these extra protons in there. I know these are electrons, but remember, for every electron, you have to have a proton.
Right. I mean, that's kind of what I was thinking too. The
So
mass of the atom
yeah,
itself.
Yeah, but we can't just say protons because this also has neutrons.
Hmm.
But if we did look at the protons, chromium has 24, molybdenum has 42, and tungsten has 74. So this only increases by what, 18? But then this increases by 32.
Hmm. So it's like
Okay,
exponentially increasing.
it's like an exponential increase. Okay, so do you see how we can look at the radius trends and combine that with uh, the mass trends based on the atomic weight and come up with an answer?
Yeah. Hmm.
Okay, let's do this one. I think we only have two more to look at.
Okay. Are you going to be having Zoom in the morning? Because you don't have
Yeah,
evenings tomorrow, right?
tomorrow at 10 and
Okay.
tomorrow at
When?
1:15.
Okay.
Okay, explain why the reaction of calcium and fluorine does not form CaF3. Okay, so we can look at this from 2 points of view. To form CaF3, we can say that, okay, calcium does form calcium 2 plus, right? And fluorine does form F minus. And when we combine the two, we do the old switcheroo. Do you remember that? So we get Ca1 and F2. And not CaF3. Are you with me there?
Yeah.
Okay, so let's answer it from the point of view that, from this point of view. For calcium F3, we have 3 F minuses, and that's okay. And the reason I say that's okay is because you have fluorine becoming F minus, which is a 1s2, 2s2, 2p6, 2p5, I'm sorry, becoming a 1s2, 2s2, 2p6. And that's what fluorine does.
Hmm.
Now, CaF3 would then have Ca plus 3, because if each one of these is a -1, what does the charge on calcium have to be?
Yeah, it would have to be 3.
Right. And so we're talking about here a calcium, which is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, would have to become 1s2, 2s2, 2p6, 3s2, and then what?
You'd have to remove 3 of the electrons. So it would have to be 1s2, 2s2, 2p5.
Nope. Take a
Wait,
look here.
what are we? Oh, you already removed it.
I didn't. Which 3 are we going to take?
Oh, we have to take it from the 4s2, and then from the 3p6, it'd be 3p5.
So 3p5.
Mm-hmm.
Okay. So we would also have calcium 3 plus, which means we would have to take 2 4s electrons and a 3p electron. And when you make ions, you are rarely going to take electrons from 2 different shells.
Hmm.
And the reason for that is because the amount of energy that is required is so different that it's not going to happen.
Hmm. Is that the explanation?
Yep. It is so much harder to take a 3p electron than a 4s that it's just not reasonable.
Okay.
It's kind of
So the
like,
amount, so basically you're saying the amount of energy required to take an electron from the 3p shell would be just 2.
yeah, compared to the 4s is
Mhm.
way too different.
Okay.
So
So
it's
it's
not
just
going
a
to happen.
lot less likely to happen.
Yeah, it's like if you're digging in the dirt and you only need a trowel to take a 4s electron. To take a 3p electron, you're going to need a cat.
Hmm.
I don't mean like a meow. I mean a caterpillar.
Yeah, yeah.
Okay, so it's
Hmm.
not going to happen. You've got a trowel. You're not going to take a 3p electron.
Hmm. So would you say that it's, so the last explanation would just be the amount of energy required would be too immense, so it's a
That's
lot
right.
less likely to happen?
The amount of energy required to take a 3p is too much greater than a 4s. And for that reason, it's not going to happen.
So it's not going to happen, or it's a lot less likely to happen?
It's not going to happen.
Okay.
Not going to happen. Do you remember how in a previous chapter we said that group 2A atoms always form a +2 charge?
Yeah, well, that's why I thought, like, maybe there's like more to this. Maybe there's like
No.
that, but then there's like
So
somewhere there's a
the reason they don't
possibility.
form a +3 is because it's just not reasonable.
Okay. I just thought you were teaching us something new. Like,
No,
oh, maybe it's
no.
maybe there's a very small possibility of it happening.
So here, the idea is very simple that the fluorines, that's okay, but the calcium, that's not okay.
Okay. So it's just a way of explaining why it is that these calciums form in 2s as opposed to 3.
Right. And I'm going to see if I can find something real quick if you've got time. Let's see. Okay, where is it? I'm going to have to close that. That's not the one I want. Close that, close that. That's not it. Sometimes you can find these maps of ionization energies for the different elements. It used to be a lot easier to find. Here's calcium. Okay, so I'm going to do a new share here. And these are the ionization energies of calcium. So let me explain to you what you're looking at. When you go from left to right, you see 0, 5, 10, 15.
Yeah.
So 0 means you've taken 0 electrons. So here where it says G2, that's the amount of energy to take 1 electron. And then you see this G1, that's to take a second electron. And you see this F2, that's the third electron. Now, mind you, this is a logarithmic scale. So because it's a logarithmic scale, it actually looks kind of nice and linear, as it were. But I want you to take a look at the first and second compared to the third. Now that third should be like way off the scale compared to the first and the second. But you see how the first and second aren't bad, but the third is just ridiculously hard?
Yeah.
Okay, so that's the deal with calcium. The third is ridiculously hard, so it ain't going to happen. And let me see if I can find something else here. I'm just not used to seeing the logarithmic scale. But here they're doing logarithmic scale again. And probably the reason they do the logarithmic scale is that to try and show you this without the logarithmic scale, you'd see the first and second, but you can't see the third because it's way too high on the graph. Does that make any sense?
Right. They're just trying to scale it so that it's user friendly.
Yeah, so if I do a new share and go back to here, if they had a non-logarithmic scale for calcium, it would look something like this. Here's 1, here's 2, and you'd have that. And then 3 would be up here. You can't even see it, it's so high.
Right. Mm-hmm.
So
Okay.
by making it a logarithmic scale, you can actually see it. Okay, so that's the answer. For calcium, you'd have to take a 3p electron, and it ain't gonna happen. So let's look at this last one. Sodium metal reacts readily with chlorine gas to give sodium chloride. What is the reducing agent in this reaction? Oh, do you remember all of that? So to get the reducing agent, we say that sodium has a 0 oxidation number. Chlorine has a 0 oxidation number because pure elements have a 0 oxidation number. And for sodium chloride, the sodium is a +1 and the chloride is a -1 because when it's an ion, the oxidation number is equal to the charge.
Right.
So can you see that the sodium oxidation number increases and the chloride decreases?
Yeah.
Well, decreased means reduced. Reduced means a rig, which means gain electrons, which also means it's the oxidizing agent. And here we have increase, which means oxidized, which means oil, which means loses electrons, which means it's the reducing agent. So first question is, what is the reducing agent in this reaction? Sodium. What property of the element contributes to its ability to act as a reducing agent? So oxidize means you lose electrons, right?
Right.
But if you're the reducing agent, you're causing reduction, which means you're causing something else to gain electrons. So here what they're really asking is, why does sodium cause other atoms to gain electrons? That's what it's really asking. Why does it want to act like a reducing agent? And the answer is because sodium, which is 1s2, 2s2, 2p6, 3s1, if it were a person or a human being, sodium wants to become 1s2, 2s2, 2p6, like neon, and become more stable. So guess what has to happen with that electron? It has to go somewhere. And when something gains electrons, that means sodium is reducing it.
Okay.
Okay, what is the oxidizing agent in this reaction? So for B, it's going to be chlorine. And then it says, what contributes to its ability to act as an oxidizing agent? And it's because chlorine wants an electron. And when it takes it, it oxidizes. And then C, why does this reaction produce NaCl and not a compound such as Na2Cl or NaCl? Well, for Na2, we'd be looking at chlorine being a Cl2 minus, which means it would then have to become, it would become
It would take away from its
it would actually add.
Mm-hmm.
So it would be neon 3s2 3p5 would become neon 3s2 3p6 4s1. And for NaCl2, we'd have to explain why does Na not become Na2 plus. And this one is a little more complicated. I'm not done finished that one. For the other one, for Na to become a 2 plus, you'd have to have a 1s2, 2s2, 2p, 6, 3s1 become a 1s2, 2s2, 2p5. And so here, a 3 versus a 2 is so different, it's not going to happen. So up here, why does that not become a 2 minus? Because it seems like putting a 4s electron doesn't seem too bad to do. And the answer is because you'd have to make 2 sodium plus 1s, 2 of them, not 1, but 2 of them.
Mm-hmm.
So that's why you don't do it.
Also, the chlorine becomes less stable, right?
Yeah, and here there's something magic about having the electron configuration of a noble gas. So this is not stable. So that's an absolute good thing to write. It's, hey, that's not stable. That's why it wouldn't happen.
Okay.
Okay, so that is the rest of the chapter. And if you want to take a look at some of the problems that we did beforehand, they're already posted in the Q&A.
All right.
And you should check them out. And I will be doing this tomorrow.
All right. Thank you, Tony. This was really helpful.
All right. You have a good night.
All right. You too. Take care.
Bye-bye.
Bye.